In this video, we're going to finally dive into the pH scale and hopefully understand a little bit more about how this was derived. So we've already seen in lab that you can determine how acidic or basic a solution is based on its pH value. But where does pH actually come from? So it's really based on the concentration of the hydronium or hydrogen ion in aqueous solution. And again, hydronium and hydrogen are essentially the same. It just depends on how you write your reaction out. So specifically, pH is equal to the negative log of the concentration of hydrogen. Or the other way we could write it is negative log of the concentration of hydronium ion, H3O+. So remember in the last video we said that water is neutral and water has a hydrogen ion concentration equal to 1 times 10 to the negative 7th. Now, if we take the negative log of 10 to the negative 7, we actually get 7, and that is our pH value. So this is where the pH scale comes from. Now, we also said that acids should have a greater concentration of H plus or hydrogen ions. So notice that as we go down towards acids, the values are getting larger and larger. So we're going from 10 to the negative 7 all the way down to 10 to the negative 1. So if we were to write this as a decimal, 10 to the negative 7 is 0.1, 2, 3, 4, 5, 6, 7. So that's a super small number. But if we write out 10 to the negative 1, that would be 0.1. So let's see. Let me double check here. So then 10 to the 0 is just 10. Or 1, sorry, just 1. Okay, so that means that our pH value is going to go from 7 to 0 for acids, because if we take the negative log of 10 to the negative 6, we get 6, 10 to the negative 5, we get 5, and so on and so forth. So that's also really handy if you're given a concentration of hydrogen ions. Usually the pH value is going to somewhat match the exponent. So it'll just be the positive version of the exponent. Now let's look at bases. So bases, on the other hand, the concentration of hydrogen ions will get lower and lower and lower the stronger the base. So our concentration of hydrogen ions is getting much, much smaller. So we go from 10 to the negative 7th all the way to 10 to the negative 14th. And again, notice if we take the negative log of the concentration, the pH is going to match the exponent. It's just the positive version of the exponent. So super handy. So let's practice calculating the pH of different solutions. So find the pH given the concentration of hydrogen ions of the following. So A, we have 1.1 times 10 to the negative 3 moles per liter. B, we have 2.5 times 10 to the negative 11th. And C, we have 4.7 times 10 to the negative 9th. And remember, the equation for pH is equal to the negative log of the concentration of hydrogen ions. So really all you have to do is plug those values in for each one and then see what your calculator gives back. So pause the video and see if you can calculate those values. Okay, so for A, we should get something that's kind of close to 3, right? Because that's the exponent. And when I plug this into my calculator, I get 2.95 as my pH. So that is really close to 3, so that makes sense. And would this be acidic or basic according to our pH scale? So it should be acidic. It's around 3. Oops, I went too far. There we go. Acidic. Now B, if we plug that value in, we should get something close to 11. So let's see, 2.5 e to the negative 11th. I got 10.60. So would that be acidic or basic? Basic. Okay. And then last but not least, negative log of 4.7 times 10 to the negative 9th. And hopefully the value should be somewhat close to 9. And my calculator says that the pH is 8.33. So that's kind of close. Now notice that as we get further away from 1, the value of the pH gets further away from the exponent. So that coefficient plays a part as well. Now, would 8.33 be considered acidic or basic? Basic, right? Although it's somewhat close to neutral, so maybe it's more slightly basic. Okay, so let's just summarize what we've learned about our acids and bases. So again, if a solution is acidic, that is going to tell us we have a greater concentration of hydrogen ions in solution compared to hydroxide ions. And the pH should be less than 7. If we have a neutral solution like water, the concentration of hydrogen ions should be equal to the concentration of hydroxide ions, and the pH should be exactly 7. And then if we have a basic solution, the hydroxide ion concentration will be much higher than the hydrogen ion concentration, and the pH will be greater than 7. Okay, so one last thing I wanted to talk about are buffers. So we actually saw an example of a buffer in lab, and a buffer solution is one that can resist a change in its pH when hydrogen ions or hydroxide ions are added or removed. So buffers can do that by being composed of certain pairs of solutes. So either the buffer will be made of a weak acid plus its conjugate base, or a weak base plus its conjugate acid. So, for example, if we look at the buffer down below, we have the acid and its conjugate base. And let's say we add more hydroxide, so more base. The base is going to interact with the acid, and we're going to form more conjugate base and water. And remember, water is neutral. Now, if we add more hydrogen ions, so more acid to the buffer, the acid will interact with the conjugate base and will actually produce more acid. So either way, the reaction is going to shift in order to accommodate the extra acid or extra base that's being added, and therefore the pH can stay somewhat consistent. So it'll probably be within a range of pH values. All right, so remember, buffers have to consist of an acid and its conjugate base, or a base and its conjugate acid, and these would all be weak. So down below I have some combinations of acids and bases, and we want to try to figure out which combinations can make a buffer solution. And we'll just assume everything's aqueous, it's all dissolved in water. So let's start with number 1. We have HCHO2 and NaCHO2. So right away, I'm noticing that we have the conjugate base of our acid. So this Na here is just kind of taking the place of a hydrogen, and we're forming an ionic compound. So this looks like an acid and its conjugate base. So this would probably qualify as a buffer. So we can say, yes, that would qualify as a buffer. Now, if we look at number 2, we have HCl and NaCl. So this still looks like an acid and its conjugate base, but remember, the acid has to be a weak acid. So let's actually write that up here. This has to be a weak acid and its conjugate base. And the opposite situation would be a weak base and its conjugate acid. Now, unfortunately, HCl here is too strong, and we wouldn't end up with any equilibrium. We couldn't go back and forth because HCl completely ionizes in solution. So this would not work. HCl is too strong. So that could not be a buffer system. Okay, let's look at the next one. We have CH3NH2 and CH3NH3Cl. Okay, so it looks like we're gaining a hydrogen between these two. So that's probably an acid and its, or a base and its conjugate acid. Oops. So let's rewrite that. We have CH3NH2 and CH3NH3. And this nitrogen would actually be positively charged, and the chloride here is just balancing that charge. Okay, so we have a base, and it gains a hydrogen to become a conjugate acid. So this would probably work as a buffer. All right, and then finally we have NH3 and NaOH. So right away, this doesn't really look like a conjugate acid base pair or a conjugate base acid pair. So yeah, that probably isn't going to work because earlier we saw that the conjugate acid of NH3 is NH4 plus, not OH minus, right? So that wouldn't work as a buffer. So again, just the main point of this example is to show that a buffer consists of either a weak acid and its conjugate base, or a weak base and its conjugate acid. So a real-world example of a buffer solution is our blood. So our blood is buffered to maintain a pH of 7.4, and that has to be unchanged because our metabolism generates CO2 um, or carbonic acid, and that's going to be added and removed by our lungs. So, for example, down below, we can see that when CO2 reacts with H2O, water, that produces something called carbonic acid, H2CO3. Now, those are in equilibrium with each other. So if we were to add more CO2, things would shift to the right and give us more carbonic acid. Or if we removed CO2, then things would shift to the left to replace that CO2 that we lost. Now there's another equilibrium that occurs with carbonic acid. Carbonic acid can decompose to produce the hydrogen carbonate ion and the hydronium ion. So our blood has to constantly move back and forth in order to maintain a pH of 7.4 as CO2 is added and removed. Now, oceans also contain a buffer system, and that's in order to maintain their environmental stability against things like acid rain. But we talked about in our carbonates lab how we're producing CO2 at a really fast rate. So it's becoming more difficult for the ocean to buffer against the increasing acidity that it's experiencing as a result. And so some aquatic life that depends on shells to live, their shells are slowly breaking down as a result of all the acid that's forming in the ocean. So even though oceans, lakes, and streams all have buffer systems, unfortunately, they can only do so much. Eventually, if you add too much acid, the buffer system just doesn't work anymore. So real world examples, I hope I didn't depress you too much with the ocean example. But that's the end of chapter 10. And we are also covering chapter 11 this week, but it's going to be a pretty short chapter. And it's on nuclear chemistry. So I will see you then.